Hi everyone. We've got a problem here on the board. We are still on the asymptotic behavior of functions. So the problem here says, without wasting time, it says let f is sure that positive integers are mapped to positive integers with f of n, that is the function we are given, f of n equals 3n to the power of 3 plus 2n to the power of 2 plus 1 divided by n. And the question now says, show that f of n is in big O, n to the power of 3, big O n cube. By what means do you show that? From first principles, we are told. And secondly, by evaluating a suitable limit. So now let's see how we go about that. If you are given a problem like this, and you are asked to solve this problem from first principles, what they want you to do is you arrive at an answer that will give you this function here, f of n is less than or equal to cn cubed for all n small n greater than or equal to big N. This condition is what it means from first principle. From first principles. This condition here. The function you are given, f of n, must be less than or equal to cn cubed, because it's cube here, that's why you have cn cubed. If it was raised to the power of 4, it should be cn4. Raised to the power of 5, cn5. This c is a constant, it's a number. It's a constant. Yeah? A number. But because here we are told it's mapped from integers, positive integers to positive integers, so this c, which is a number, it got to be a positive integer. So that's condition for number 1. Number 2, which says by evaluating a suitable limit. What that means, we take the limit of this function, because asymptotic behavior of function, that's actually what it means. You try to predict how the function will behave if you keep on adding the unknown in the function. Like if you keep on increasing the inputs to the program, how the program will behave. Is it going to crash, going to be slow, or do something else? So that's what we're doing here by finding limit of a function. So what you are evaluating here, a suitable limit, what you need to find is an integer. First, the number has to be positive integer. Positive integer. Then it has to be finite. It has to be a whole number. Countable, something you can count, a whole number, not a decimal number. Number with a decimal point, not a fraction, not a real number, not a complex number. It has to be a real, a finite, a whole number. So, if that is the case, now let's move on to solve the problem. We got f of n equals 3n to the power of 3 plus 2n to the power of 2 plus 1 all over n. Now we want to start solving from first principles. And we want to make a claim from here that n cube, since we are asked about n cube here, must be less than or equal to 3n cubed plus 2n squared plus 1 all over n for all n greater than or equal to 1. That is, if we choose n here, if we choose a number from 1 and above, 1, 2, 3, 4, 5, 6, 10 and above, and we now substitute that number for n. Whatever that number is, this condition will always hold. If we put 2 here, this is going to be 8. This 8 is less than what is inside here. If we choose 3 here, this is going to be like 27. That 27 will be less than what is going to be here, this function. So that's the condition we are trying to explain here. But our aim to arrive at this answer, this correct answer here, is for us to compress this function. Now it has 1, 2, 3 elements. We only need one element, C, N. This is what we need, a constant and the unknown. This is what we need, Cn. In this case, Cn cube. Yeah? So we've got to try to bring this equation to only 2 things here. Let's carry on. We can now say that n cube is less than or equal to 3n cube plus 2n squared plus 1. Still, this condition holds for all n greater than or equal to 1. The condition still holds. We can further say that n cube is less than or equal to 3n cube plus 2n squared plus n. The condition still holds for all n greater than 1. As long as we keep on using this condition here for all n greater than 1, this condition here holds true. So we can carry on. We can say that n cube is less than or equal to 3n cube plus 2n squared plus, this was n, now I put it n squared. Condition still holds. And now we have 2n squared here. So let us just do it quickly. This is 3n squared. Because 2n squared plus 1n squared is 3n squared. Now we have 3n squared, 3n cubed plus 3n squared. Just for this. Now we still have our claim n cubed is less than or equal to 3n cubed plus n cubed. I'm changing this one now from 3n squared to n cubed. For all n greater than 1. I'm still making the claim that as long as this n is greater than 1, then this condition is true. If that condition is true, let me put it here clearly so that you can see it's for all n greater than or equal to 1. If this condition is true, then I can do anything in this equation as long as I'm within these boundaries. N is equal to or greater than 1 and n cube is less than or equal to this. As long as I'm within that boundary, anything I do here is correct. So if that is the case, I now want to claim that n cube is less than or equal to, this is 1n cube, 3n cube, 4n cube. Now you can say we have arrived at the answer because all we needed to do just to find 2 elements, a constant and n cube. But for this one, for all n greater than big N, that is, whatever n we found, we put here, as long as it's greater than big N, this condition is always true. And what is our n? Our n now, our C in this case, as we said before, C now is 4. So what is our n? Our n has to be any number greater than 4. Our n has to be any number greater than 4. Then this condition will hold. So this solves the problem. Part 1 is done. Now let's jump to part 2 quickly by evaluating a suitable limit. That one is up here from first principles. Let's go to the second one. By evaluating a suitable limit. That's what the second one says. By evaluating a suitable limit. So, now we can say the limit LIM, we say, as n tends to infinity, 3n cubed plus 2n squared plus 1 all over n. So what do we do here? There are so many methods to apply when you are doing limits. But sometimes you look at the problem, then you choose a suitable limit method you can use to solve the problem quickly. So here, we can say we divide everything here by n cubed. Everything here by n cubed. So therefore, you will have now the limit as n tends to infinity. You will have here 3n cubed all over n cubed plus 2n squared all over n cubed plus 1 all over n cubed. When you do like this throughout the equation, you haven't changed the equation at all. It still remains the same because you are dividing by a common number. All the functions involved in the equation. So you haven't changed it. It still remains the same. So now this will give us the limit as n tends to infinity. N cubed, this will cancel. We'll get here 3 plus n cubed, 2n, you will have here 2 all over n, plus 1 all over n divided by n cubed, you will have here 1 all over n raised to the power of 4. This is what you get. This is what remains. So now, when n becomes bigger and bigger, what do you get? 2 divided by 100. It's going to be very, very small. 2 divided by 1,000, further smaller. 2 divided by 1,000,000, if n keeps getting bigger. So this number will approach to 0. This one will approach to 0. So what is left is 3. So the limit as n tends to infinity, what you have is just 3. And this 3, now, 1 is positive, 2 is integer, 3 is finite. So it satisfies all the conditions. Finite, positive, integer. So that's your answer. The answer is 3. I hope you enjoyed this lesson. Thank you.